Hello. In today's video lecture, we are going to be looking at digital signal processing in the context of digital control systems technology. So we will not be going into very much detail into digital signal processing, but we will look at some of the aspects of digital signal processing that is relevant to when we are building digital control systems. So what do we mean by digital signal processing? In one of the previous lessons, we have discussed about analog signals, digital signals, and then analog to digital conversions, digital to analog conversions. So we have discussed about those so far. But once we have these signals converted into digital signals from the external world, if we use some computational component, a computer, a microprocessor, a microcontroller, and then we do some processing with that digital information. If we do some computations with that digital information, the digital signal, then that is essentially what we mean by DSP or digital signal processing. Then the same life cycle of signal as we discussed previously continues, that we may convert the outputs of such a DSP or the digital signal processor into another analog signal through a digital to analog conversion. So that is possible. But what we are concerned about in today's lesson is this processing part or the digital signal processing part. There can be a number of ways such digital signal processing can be used. So there would be some systems where the information would start in the form of an analog signal. Then after some processing, the output also may need to be some form of an analog signal. So that is possible in some systems. An example would be a sound recording. So you may record the sound in the physical environment where it may originate as an analog signal from a microphone. Then we could record it digitally, do some processing on it digitally, but then again, if it's played back through a speaker, again we may need to do a digital to analog conversion to produce an analog signal that can be fed into a speaker to produce the sound. So in the case of a digital recording of music or sound, there we would use digital signal processing, but we would also have analog signals from the beginning and analog signals at the end. There could be certain other systems where we may start with analog signals. So we may start with analog signals, but the digital information that we receive at the digital signal processor is all that we need. We could say, even if we take the example of recording sound, if you are just recording a sound and keeping it as a sound file on your computer, then there the digital to analog conversion is not happening. So that part is not happening. So the information stays at this point itself. Then another third variation is, if we take an example, something like a text to speech example, the text would be produced inside the computer. So inside the digital signal, inside the computer as a digital information that would be fed into the digital signal processor to produce suitable digital signals. Then they may be converted into analog signals, and then those are reproduced through a speaker. So the main thing that we can see here is not all conversions have to start and end from analog to analog. There can be certain information that may start as an analog input, end as an analog output. Some may start as an analog input but end as a digital output. Some may start as a digital input but then end as an analog output. So we could have all of these variations depending on the systems that we are using. So the next question would be, why do we need DSP or digital signal processing? Many of the operations that we would see as relevant to digital signal processing can also be done using general purpose microprocessors. When I say they can be done, what I mean is they can be theoretically done using any microprocessor. But if we need certain level of performance, certain level of computational capability for certain specific type of tasks, these general purpose microprocessors may not be capable of doing that because they are not built for those specific tasks. So things like audio information, audio recording, audio signal processing, communications, network communications, wireless communications, image manipulation, graphics processing. So these type of operations would have specific functional requirements, specific data requirements, specific speed requirements. So specific underlying operations. So all of these things would be there. If we go on to build these operations using general purpose functions found on general purpose microprocessors, those operations would take more than a few clock cycles. Whereas if we build these special functions specifically in these special purpose processors or DSP processors or digital signal processing processors, we can build these special functions, and then we can make those special functions perform in a single cycle. So one of the main things that we would try to achieve is making these special functions perform in a single cycle. So that can lead to us having much faster specific functions compared to if they were implemented in a general purpose processor. Say for example, if we think about a graphics processor that is going to produce some output onto the screen, if we use our general purpose processor, the same functionality can be built, but it will take much longer to do the processing, so the outcome will be much slower, so we may not have the performance that we expect. But if we use a specific GPU or graphics processor, a specialized DSP for that purpose, it can have those graphics specific functions built in as the main operations, so then it can use those and do the same function much faster compared to a general purpose processor. So that is the main reason why we would use DSPs in building various systems. And as I said, the common types of systems where we may come across DSPs are things like communications, networking, wireless communications, graphics, image manipulation, audio processing, video processing. So these are some of the places where we would find the use of DSPs. So in the case of sound applications, we can use DSPs to do compression, various special effects, sound recognition, so like speech recognition, things like that, or even the reverse of text to speech generators. So these can be used in like cell phones, MP3 players, like various places, various devices would use these type of chipsets. When we think about communication, you may come across some of these concepts when you are studying networking, things like modulation, coding, detection, echo cancellation. So these type of things again can be used in any sort of communication devices and so on. There can be a lot of specialized functions built specifically for vehicles, like in automotive applications like ABS, braking systems, GPS specific things, cruise control, parking sensors, or automated parking capabilities. So again, these things can be built inside these specialized DSPs for that particular application. So one of the common things that you would find with DSPs is that a lot of them would be sort of very specifically designed. So you will have to think about the suitability of a particular DSP for your necessary application. Whereas in general purpose processors and microcontrollers, we didn't have that level of restrictions in terms of what we can use where. Whereas DSPs, we'll have to think a bit more in terms of whether a particular DSP is the suitable one for a particular application. Then even much more complex applications are coming along these days in medical applications, in electrocardiograms and things like that, military applications in remote sensing, radars and things like that. A lot of DSPs being used in image and video applications, a lot of mechanical DSPs to control motor controllers, various processor controllers, all these things. So again, a lot of different applications where a lot of DSPs are being developed and DSPs are being used these days, because they can do these specific functions, because they are designed for a very specific function in a much more efficient manner, in a much more faster manner, in some cases even with less power consumption and things like that. So they have a lot of those advantages as well. So when we think about those advantages of DSPs in a bit more detail, the accuracy of the outcomes would be a significant one, because when we use digital circuits, they are less sensitive to interferences and tolerances of other components. So we can get very high accuracy. This is particularly true when we are when our alternative is to using some analog system. Using the digital systems would be much better there. Can be cheaper, because when the economy of scale and things like that would dictate that we don't need a fully fledged microprocessor, but rather we can use a simple DSP for that specific application, because that's all we need. So then we can have it done cheaper. So if you think about it, rather than using a typical microprocessor that is found on a computer or PC, for example, we can use a much cheaper audio processor, for example, in an audio player, and then the effective cost of that device would be significantly less than using what is a general purpose processor. But still, by using DSPs, they are still processors, they are still microprocessors, but with some specialist functions. So we can get the advantages of programming these devices. So we can have flexible functionalities, flexible configurations. So we can configure these devices as we need, depending on the functions that are available and so on. So those can be a very good advantage. When we work with DSPs and when we are working with digital signals, we have the advantage of storing the information, storing these signals that we are processing in a digital realm. So, and then we can even reproduce these signals as many times as we want. A good example for this could be, even if we take an example of an audio, digital audio, and on the contrary, if we think about an analog audio format like a tape drive, or a cassette tape, or even a vinyl record, all of those type of mediums have the tendency to lose the quality of recording over a period of time, whereas the digital signals, if we store it in a very good quality at the beginning, the quality doesn't change over a period of time, and we can reproduce the same sound as many times as we want without any loss of quality there. And one of the other advantages would be because we are doing these things inside DSPs. DSPs are microprocessors, so then we can do programming and we can do complex programming. So we can compare to building custom circuitry or other hardware implementations. When we build these functionalities inside DSPs, again we can build fairly sophisticated signal processing algorithms in a much easier manner, depending on, again, given the DSP supports those implementations, but we still can do that. So these are some of the common advantages for using DSPs in building various types of systems. Then when we think about disadvantages, one of the disadvantages that we discussed when we were talking about digital and analog signals, and when it comes to digital signals, they may require a very higher bandwidth compared to the same amount of information being transmitted in an analog form. There are a lot of advantages to transmitting information in digital. Things like noise interference and things are much less, but still we would require a higher amount of bandwidth if we want to transmit as a digital signal or communicate as digital information. So that could be a disadvantage depending on our application. Then the speed of those processors would dictate how fast we can do conversions. So if we have an analog signal that is very significantly fast changing, sometimes the conversion into digital realm may be challenging, and we may have to use some more advanced or more sophisticated DSPs to achieve that. So not all DSPs would be equally capable of doing everything. We may have to, as I mentioned previously, we may have to choose the most suited approach depending on our requirement, economy, the budget, and all these things will influence in terms of the choice of a suitable DSP for a particular application. Then we have the problem that we had with digital signals, that is, some information is going to be permanently lost when we are going to translate from analog signals into digital signals. So then whatever the processing that we do inside a DSP is going to carry on that disadvantage. So the disadvantage of that is coming from sampling and quantization losses is going to be there when an output is being produced through a particular DSP as well. Then another problem is most of the time once we do this conversion, once we operate these things in the digital realm, there's no way of getting back those lost information that we had in the analog information. Then in addition to that, sometimes depending on the nature of those signals, again the dynamic range of the conversion, the dynamic range of the DSP, so that is what is the smallest change it can detect to what is the largest change it can detect. So depending on these systems, they may not be satisfactory catering to both ends. So these are some of the common disadvantages that we may find with many DSPs. Now let's look at the sort of an overall architecture of a DSP. And in many cases, how we may find this is the DSP itself will have the analog to digital and digital to analog conversions built into that. So the DAC and the ADC are mostly built along with the DSP. Sometimes maybe even available in the same chipsets. Then, as with any sort of microprocessing component, it would need some memory for where it can hold data and instructions for processing. So it will need some memory. So it is like any other microprocessor, all the instructions and data that is coming into the DSP will have to be stored somewhere. So it will need some memory. Then it should, depending on the type of DSP, it should also support some ports so that it can be connected to the external world for various signaling and things like that, either through serial ports, parallel ports and things like that. But it can have some communication capabilities depending on the type of the DSP. Then in addition to that, when we think about the actual computation aspect of a DSP, this can be done in two places. We can have an ALU, an arithmetic logic unit, where most of the major functions can be implemented. In addition to that, it can also have an auxiliary ALU where some other operations can be performed in parallel. So, depending on the nature of the DSP, we can have a number of different ALUs doing number of different processing operations at the same time in parallel. So that is the basic architecture of a DSP. So if we think about it, this architecture is not significantly different from the architecture of a basic computer. The main difference being the DSP is the microprocessor, then we have some memory and input output happening along with that. Then when we think about DSPs and how we can access or use a DSP, they can be available as in sort of three main different forms. The hardware component of DSP can be available in three different forms. The first one is what we call as a core. So when we say a DSP is available as a core, what we mean by that is, it is the DSP components are made available as that particular hardware design, then which can be incorporated into some other processor design. So the DSP functionality is available as a core, then that can be added onto various other components and built as a overall design. Then we can have what is called a processor. So when we think about a processor, in a processor, all the other components are also included along with the processor. In a core, only the main DSP specific components are there, other parts needs to be added. In a processor, all these other key parts are also combined with the core, and that is a processor. But one of the most common ways that we could access a DSP and we would come across a DSP is what we call as a board level product. So this is where we have the DSP along with converters, some other input output capabilities and various other things on a single board, and that is available as that. So these can be sometimes microcontroller development boards. Some of them can come under this category. Things like a graphics card or a sound card for a computer can be categorized as this, because it has a lot of these other components attached along with that microprocessor and core components in addition to these. So these are sort of three form factors in which we can find DSPs from a hardware point of view. So when we think about using DSPs or digital signal processing, the main sort of techniques, type of techniques that are used in most DSPs is what is called the divide and conquer strategy. And this divide and conquer strategy is normally called superposition. The idea here is a particular signal that is being processed will be broken into single component or simple components, and each of those simple components are processed individually, and then the results are reunited. So that is the idea behind superposition or the divide and conquer strategy. So we break a problem or a task into a number of subtasks, and then each of those subtasks are performed independently or individually, and the results are then combined to produce the final outcome. The main advantage here is when we have a fairly complicated task or complicated problem that is now broken into many easy problems. So instead of processing a single complicated problem, we can process many simple problems much faster. So that is one of the main reasons or main ideas behind this approach. But sort of the only limitation in terms of using superposition is it can only be used in systems that we identify as linear systems, which means should satisfy certain mathematical rules. So that is, we can breaking them into those parts and operating or computing them independently and combining them produces the same output. If that is satisfied, then that we call that as a linear system. So to use this approach, we should have that. So say if we start with a problem and we break that into 3 sub-problems, and then we find the solutions, and now if we combine those, is it going to produce the final solution for the whole problem? So if that is matching, so then we can say we can use this approach there. But the advantage that we have here is most of the applications or problems or systems that we would encounter in most of the science and engineering applications, they fall under this category of linear systems. So that is why we can use this approach in many DSPs, the superposition approach or the divide and conquer strategy, where we break things into simple components, process them individually, and combine the results, whereby we are only processing many easy problems rather than a single complicated problem. So when we think about using this technique or this strategy, we have to think about 2 main sort of concepts here. One is called synthesis, the other one is called decomposition. So the idea of synthesis is, when we talk about synthesis, what we are doing here is we are taking a number of signals. So say we are taking a number of signals and then we are combining it into a single signal. So that is synthesis. So that is, synthesis is combining multiple signals. On the other hand, when we talk about decomposition, we are talking about breaking a signal into multiple signals. So if we take a single signal, with decomposition, we will produce a number of signals as an output, or we will break them into that. So these 2 approaches are necessary for us to use this type of DSP approach, where we can break them and combine them. To do that, these 2 techniques will be necessary. So the concept of synthesis and the concept of decomposition, whereby we can combine multiple signals or we can break a signal into multiple signals. Then when we think about DSPs, one of the main things that we identified is DSPs are not that different from any microprocessor approach. The main difference is it has some special functions. Beyond the special functions, it is a microprocessor. So it is like any other microprocessor. So what we can do with digital signal processing or DSPs is we can use them in many ways similar to how we would use a microprocessor. So when we think about programming them, we can use high-level programming because it is easier to program that way. We can use assembly language type low-level programming to achieve much faster execution. The same applies in general computing realm as well. Or we can combine these approaches of DSPs or rather assembly programming and high-level programming depending on our application. So some time critical, some where we need high performance things, programming them in assembly, and then certain other features that are not so time critical, programming them in high-level languages. But in general, the basic programming approach that we would use for DSPs is the same as the programming approach that we would use for any microprocessor. So the only difference is going to be a particular DSP is going to have a number of specialist instructions compared to the general purpose processor's instruction set. So if we take a general purpose microprocessor used in a laptop, it will have a set of instructions, an instruction set architecture. Similarly, a DSP would have its own instruction set architecture with the specific instructions for those specific functions it provides. Say for example, if we take a communication specific DSP, it will have functions for modulation, encryption and things like that. If we take an audio specific DSP, it will have instructions relevant to audio processing, signal processing, synthesis, filtering, noise cancellation, things like that. So some of these capabilities will be implemented as low-level DSP instructions. So those can be directly used from a programmer's point of view. Other than that, the general programming approach can be thought as fairly similar to how we would use with any other microprocessor computing environment. Then when we think about using DSPs and building systems using DSPs, we will come across a number of different tools. Things like simulators and emulators. So simulators are things where we have a software implementation of a chip. So in a simulator, we have a software implementation of a chip. So we can try out something without even having any hardware. So without having any hardware components, we can do the same testing, same trying out with the use of these type of simulators. In one of the upcoming lectures also we will talk about using simulators as part of some of your practical activities and things like that. When we talk about emulators can run some of the functions inside a computer, but then they can do the actual processing on a DSP. So the actual processing will be done on the DSP, but the inputs and outputs will be sent and received back from a computer. So we will have much more control over what is happening, and this can be used for detecting errors, figuring out what is happening and things like that. So that is a different approach. Whereas in simulators, everything is happening inside a simulated software environment. With emulators, some of the things are happening inside the software environment, and some of the things are going to be actually happening in the actual hardware itself. Then other than that, we may use things like a debugger, which we can use if you would be familiar with using software debuggers to figuring out errors in your software. So you would have studied that in various programming modules. So a similar approach can be used for DSPs as well. So there are tools known as debuggers, so they can do the same functionality again, doing the executions and controls happening in the DSP, but the results being fed back into the PC, so some observations can be made and errors can be found out. So that's all for us in today's discussion about digital signal processing. If you have any questions, please post them on LMS or communicate to me using usual communication channels. Few more information will be shared on LMS as well, and also pay attention to your project progress. Again, more information on that will be posted on LMS. So until next time, thank you for joining in this lesson, and goodbye.